This video is an introduction to the orbits function of Speckle ToolBox version 10.06. The first thing you should do is download a copy of version 10.06. If it comes as a zipped file, then extract the files. I have put it in its own directory. And you should have 4 files. There's the application file and 3 other files. If you compare the number of files to version 10.03, you'll notice that there are actually 5 files in version 10.03. And that's because in version 10.03 there is a file called ORB6 orbits, an SQL file. And this file, if we double click it, you can open it with a text editor like Notepad. This contains all the orbital parameters of the systems listed in the 6th catalogue of orbits of visual binary stars from the Washington Double Star catalogue. Now, in the past, if these orbital parameters were out of date, you would have to go to the Washington Double Star catalogue, get the latest ORB6 orbits.sql file, and then copy and paste the new orbit into this file and save it. However, I think things are different in version 10.06, in that if we go back and have a look at 10.06, there is no orbits file present here, and it appears that Speckle ToolBox actually reads the orbital parameters from the historical data file that you obtain from the Washington Double Star catalogue. So let's have a look at version 10.06, and we're going to study a particular star system, Dunlop 5. So this system has a grade 4 orbit in the 6th orbital catalogue. This is the Washington Double Star historical data file, and you can see the measurements here back from 1825 through to the last measurement they have here in 2019. But I've observed this system and written a paper on it, and so I have a measurement from 2024, which we're going to incorporate into the program. Notice here you can see that there are the orbital elements present here, the period, the semi-major axis, inclination, etc., eccentricity, and you can see it's a grade 4 orbit, and here is the reference NAP 2020. So this is the orbit as it appears in the 6th orbital catalogue. Okay, we're going to reduce that. Now let's open Speckle ToolBox version 10.06. I've created a shortcut on the desktop that allows me to run the file from there. So we go to Orbits and Read Observation File. The file that we're going to read is the historical data file. And here comes the orbit. The apparent orbit is shown here, and here are the orbital parameters. As shown here in the historical data file. Just want to move this slightly. You may notice that the historical data file and the orbit associated that's given with it looks different to the orbit in Speckle ToolBox, and that's because the axes are labelled differently. In Speckle ToolBox, the north axis is the x-axis and the y-axis is the east axis. But in the standard view from the Washington Double Star catalogue, the x-axis is the east axis and the y-axis is the north axis. So if you look at the Speckle ToolBox orbit, if you rotate the image 90 degrees clockwise, then you will get the same image that you get with the Washington Double Star Catalogue orbit. So it's just a question of orientation, but it can be confusing. So let me just reduce that. Right. Now, I did a study of this system in 2024, and I'm going to add an observation file here. This is an Excel file that has my observation in it. And this little square that's just appeared is actually my observation. So if we right-click that, you can see that the decimal date is 2024.895. There's my initials, and it was done with Los Combres Observatory, and C means it was a photographic method using CCD/CMOS. So let's see how my data fits in with the proposed orbit with these orbital parameters. So what we can do is we can generate a position where the orbital parameters predict the secondary to be at decimal date 2024.895. And let's just have a look. Just remember this program does have a lag phase to it, so you have to be a little bit patient with it. So let's generate a position of the secondary using these orbital parameters for the decimal date 2024.895. And it's changed. Let me just zoom into that. So you can see this is my observation here, and this is the distance in milliarcseconds from where the program thinks it should be if it was to fit on the orbital diagram. Let's just have a look here. So I'm 130.38 milliarcseconds away from that position, and my position angle was 184.65 degrees, and my separation was 11.321. The last measurement here was 2019 by NAP, and it's shown here. Now, Speckle ToolBox, let me just reduce the orbit. So these are all the historical data points present. Speckle ToolBox will only show you the most recent ones in these columns here, in the color-coded. So C would be photographic method, MA is a micrometer method, HG is the Gaia satellite data, and you can get the meaning of these letters from the Washington Double Star Catalogue notes. So let's talk a little bit about optimization. Optimization is a very complex topic, and I can only give you a very brief overview and introduction to it. Now, Speckle ToolBox can use an algorithm to try and work out the best orbit for the data points that it has. Now, you can give weight to these data points. I would recommend initially leaving them at 1. People can play around with these and give various weightings to data points. By that I mean, by giving them weight, you're giving them more importance. So you might say that the Gaia data or the photographic data is more accurate than the micrometer measurements. But I have yet to see a detailed study on how to weigh precisely the various components in optimization. So I leave it at 1. The other thing is that you may have data points that are outlying. For example, this one here, let's have a look. This is Dunlop's measurement in 1829 of this pair. Some of Dunlop's measurements were actually just done by eye, not with a micrometer. So maybe you don't want to include this measure, this data point, into your optimization process. So you have the option here of don't use in optimizer. So we can click on that and you'll notice a blue circle will appear around it, and that data point will not appear in the optimization process. So in optimization, we are going to try, our aim is to reduce the WRMSD, or the weighted root mean square deviation, to the lowest value we can get. And you can run this program for many iterations. I usually run it for up to 2 million iterations, and then I'll run it several times. And it's suggested that the orbital parameters you get with the lowest WRMSD are the ones you should take as the new orbital parameters. So let's have a look and have a go at optimization. So we've excluded this data point here. We've added my data. These are the current orbital parameters published in the Washington Double Star Catalogue. The WRMSD is 252.39, and I'm going to click on Optimize. And immediately you can see it drops down, starting to drop down. So I'm going to pause this video now and come back when we get up to about 2 million iterations of this program. Okay, so I'm back, and we've let the program run for over 2 million iterations. Actually, there was very little change after about 1 million iterations, but I let the program run to get up to 2 million. You can see that the WRMSD is now 248.288, and these are the suggested orbital parameters. If we look at the orbital diagram, the blue is the apparent orbit based on the original orbital parameters, and the orange orbit here is the new orbit with these orbital parameters. So as I've said, optimization is a complex and very interesting topic. There are a number of videos present available from Boyce with discussions with Dave Rowe about optimization, and I refer you to those. Thank you for your attention.